Welcome everyone to the third and final installment of, hold on, there we go, okay, no one saw that. The third and final installment of Dave Does Pre-Calculus from Home about complex numbers in polar form. This is the last section we're getting videos for this semester, and this is the last video in that section. I'm kinda gonna miss you. There'll be more opportunities for videos, I'm sure. Summer semester is fast approaching. Anyway, I wanted to start with an example of the kind of stuff you'll see on the homework. It's going to look a lot like this. You're going to be given two complex numbers in polar form. You're going to be asked to multiply them. So z1 times z2. And to do these, time me, right? We're 54 seconds into the video. Let's see how long it takes me to do this. 5 times 2 is 10. Pi over 12 plus pi over 6. Oh, we need a common denominator, so this is actually on the more challenging side of things. Common denominator I think should be 12s. So this pi over 6 is secretly just a 2 pi over 12. So pi over 12 plus 2 pi over 12 is 3 pi over 12, which is pi over 4. So cosine pi over 4 plus I sine pi over 4. And that's it, you're done. I'm now at 1 minute and 33 seconds, so this is a 40-second problem, and this is on the harder side of what you'll have to do in the homework. That's good news! That means that this is going to go really smooth, and everyone's going to do great on this homework and get good scores. So that's the kind of example you'll see a lot of. I do want to do more examples of what I did in the last video, where I do it, I like the examples where I get to do things both ways, where I take an angle in rectangular, or not an angle, I take a complex number in rectangular form and I multiply that out, and then I convert that into polar form, and I multiply them in polar form as well, and I make sure that I get the same thing both ways. To me, there's a lot of value in doing things two ways and seeing that you get the same answer. It's like a verification sort of thing. And I like verification sorts of things because, honestly, you have no real reason to trust me about de Moivre's theorem. I've told you many times not to trust me in general. So this is a good practice for not trusting me, trusting the mathematics instead. So I'm going to do a problem like that. I want to do that problem using 3 minus 4i. So the first thing I want to do is convert this into polar form. So r is going to be the square root of 9 plus 16. So that's 25. Square that should give me 5. And I need a theta as well. Tangent of theta equals negative 4 over 3. This is not on the unit circle, so we're going to have to use a calculator to approximate this, which we've sort of already done in the first video. When it was positive 4 over 3, we got positive 53 degrees. It's negative. We're probably just going to get approximately negative 53 degrees. That's what we should be expecting from this. So I'm going to put that in there. Cosine of negative 53 degrees plus I sine negative 53 degrees. I think the red is just about done. Let's slide on into another color as I find the polar version of another point, another complex number. Next I want to do plus 5i, I think, is the one that works out nice. Yep, 12 plus 5i is the one I want to do. So, once again, I'm going to get some, I'm going to convert this into polar. R is going to be the square root of 144 plus 25, which should give me the square root of 169, which is 13. So I'll have a 13 times the quantity. I need a theta. The tangent of theta is 5 over 12. I just checked with my computer over there that this is another calculator arctangent problem, because 5/12 is not on the unit circle as a tangent value. So for this one, we're going to look at theta being about 23 degrees. So I'll put that in here. 13 times the cosine of 23 degrees plus I sine 23 degrees. So I have two complex numbers. I have them both in rectangular form and in polar form. I'm going to multiply them in both forms, make sure that I get the same thing both ways. That is today's plan. I'm going to clean this up a little bit as well, because that looks messy to me and it probably looks worse on a camera. Let's see if the red is behaving a little better now. Negative 53 degrees plus I sine negative 53 degrees. Okay, this is what we're looking at. Next up, I'm going to start doing some math on these guys. I want to multiply these things together in rectangular form first. So I'll multiply this by this, and I should get 48. No, not 48. 36. Let's start with the 36. 36 from the front term. The middle term should give me negative 48i from this, and plus 15i from this. So this is the first, the outside, the inside, the last should give me negative 20i squared. Yeah. Okay. So now I need to do some conversions. Negative 20i squared is positive 20. Positive 20 plus 36 should give me 56. And this should give me negative 33i. So let me see what happens if I convert this into polar form. Or, no, I want to do it the other way. I want to do this multiplication in polar form and see if I get something similar. So, I'm going to erase some of this blue stuff so I can create some distance. In polar form, this multiplication should be the product of these guys, which should be 65 times the cosine. Negative 53 plus 23 should be negative 30 degrees plus I sine negative 30 degrees. And now I can see what I get. The cosine of negative 30 degrees is about square root of 3 over 2. So let me get a decimal approximation for that. about 0.866. So, cosine of negative 30 degrees is approximately 0.866. And again, all of these things are sort of approximations on this end. But it's not exactly 53 degrees and it's not exactly 23 degrees here. Both of these are rounded. So this is also an approximation. The sine of negative 30 degrees is negative 1/2. So that's nice and convenient there. The product of 65 and 0.866 is 56.2. And 65 times negative 1/2 is negative 32.5i, which is approximately equal to 56 minus 33i. So checks out. Both ways I do this, it's giving me approximately the same answers. I can do it in using FOIL on the rectangular method. I get 56 minus 33i. This is the exact answer. If I do approximate polar versions, these are already approximate because of these angles are rounded. If I do approximate polar versions and then multiply those using de Moivre's theorem, I get this. And if I convert that back into rectangular, I'm getting 56.2, which is almost perfect. 32.5, which is almost perfect. This is a certain amount of rounding error can be expected because of these approximations. But this is a pretty good accuracy. So this has been my example of converting coordinates into polar form, multiplying them both ways using de Moivre's theorem, converting that polar form back into rectangular to check my answer. This is the whole package. The entirety of section 7.3 in one example. There is one last thing that I need to talk about before I end this video. Honestly, I should have talked about it right at the start of the first video, but I forgot. It's pretty much just a vocabulary thing. When we are finding, when you start with an angle like this and you find what I've been calling r, square root of a squared plus b squared, I should warn you that this is considered the absolute value of 3 minus 4i, which may seem like a weird word to use to describe. Like, what does absolute value mean on a complex number? An absolute value means distance from 0. That's what absolute value has always meant on the real number line. That's why it makes things positive, because distance is always positive. And in the complex plane, it still means distance from 0. It's just in this case we have to use the Pythagorean theorem to get that distance. So this is called the absolute value. Sometimes it's written as r. Like if this is called z, sometimes you would write this as the absolute value of z. So that's the vocabulary. Should have mentioned that earlier. Sorry about the poor timing, but that's it. That's the whole thing. We are finished with Chapter 7. We are finished with pre-calculus at this point. All that's left is an exam.